a song that is No Man's Land. Well, man being used in the general form of like human. Alright, so, again, we are still in 8th grade content. We are going to be doing specific Desmos type review and test type prep Wednesday, Thursday, Friday of this week, but we're still trucking along through our content right now. So if you want to whine and complain about homework, you can bump down into the Math 7 class, and then you will have already done that homework, and you can stop your whining.
Wait.
No one has to do that.
If you can't handle the fact that we're going to have homework till the very end of school, you're not in the right class.
I was saying, like, I said I can't, oh my god.
Alright, moving on. So that hopefully I can give you time to work on the homework during class today. Can I help you, bud?
Oh, I was looking for the pencil
I don't know what happened. Somebody stole it. You might have to go over to Goldberg's room. I know, it got stuck. So, what we did last week, those transformations, did it change the size of the key? No.
Wait, what were you doing?
Calm down. We're chill. Last week, the slides that we did with the key and the lock puzzles.
Oh, yeah.
Your guys' memory is top notch. Long weekend, I guess.
I wish.
I'll give you and Luke Goldberg's and everything. So, the key did not change size, right? Key change size, all we do is move it. That is called a rigid transformation. What types of rigid transformations did we see last week? What different sort of things could we do to the key?
We could reflect it.
Hands.
There was rotation. Oh my god.
Okay, so can you tell me what rotation does then? Can you tell me what rotation does?
Like switches 90 degrees and 180 degrees.
Turns, either 90 or 180 or, different directions, clockwise or counterclockwise. Alex?
There was also a moving one where you had to like put coordinates.
What do we call that? The moving one. Starts with a T. It's the same thing you do with language, to move from one language to the next. Translate. So you translate are your slides, right? Translations are your slides. Now, Alex even told us where you put the numbers in, right? Like X plus whatever, Y plus whatever. So we have rotation, translation, and we had reflection. What did it need to do a reflection? What else did we have to tell it? Give me hands. Somebody who can explain it. No? Okay. Yeah. So your reflection has to either tell you an axis or some other line to be flipped across. Okay, why were you sitting here singing and just wasting time, and then you leave to go to the bathroom? That's a big issue. Plot those points on your graph paper. So to set up a little XY axis. Now I'll warn you, we are also then going to double those points. So we're going to plot those points, and if you want to use colored pencils, you may grab some colored pencils and color code this for your first set in one color and your second set in another color. Yeah.
I had a question about this one.
Okay.
Okay, so how does the -1 and the 1 and all that work? Like,
You mean the negative one?
it over Y and X?
Yeah.
And then it reflects it over Y and X.
There's also colored pencils there in the resource.
No, they're not. Wait, where is it?
Um,
I found it. I found the blue one. How big should our current plane be?
so,
Like,
well,
how big
your that's a
yeah, okay, so I can, what's that, like, how you're adding one?
So this is not adding or subtracting. This is determining what location your line has. So is it going to be X, Y, or Y line is determined by do I want to reflect vertically or horizontally?
Yeah, I got that. I mean, like, you know how it's y equals and then the
Yeah, but so negative would be a line down in the negative. It's not minus, it's a line on the negative. So this is in the way here, but if I do a flip like this, and I do it across a negative, again, it's just a line in the negative. But if I am translating and I go negative, that moves left or down. So, left or down. Wait.
Which problem is this? It's 42. What? 42. 642. 642. Oh, that's fine. That's why. CC 1.2. 4.9.18. There we go. Oh, man.
So we have 2, 1, 3. What are you doing, man? Yeah. Yeah, I mean, I got a paper cut, I got scissors back there. I have like 8 pair of scissors up here if you want. I only got 1. So we got point 2, 3, 1, 5, 5, and 2, 5. So plot the following points in graph paper, connect them, make a quadrilateral. Sorry, line should be straight. My smart board is a little rogue. Then double every value. Every X doubled, every Y doubled. If you're a color coder like me, change your colors. Graph those points. Don't erase, don't change. Graph an additional 4 points at locations double the locations you started at. Same graph, same coordinates, same everything. I told you guys, make it big enough, we're going to double this. So you aren't listening to directions. Sorry guys, at the end of the year, like, it's April. I'm not in the business of repeating myself 7, 8 months into the school year. So.
Oh no. Seriously.
Okay.
Mine looks really cool. Mine looks the same. What's it picture?
Get a straight edge. If you don't have a straight edge or something that you can draw straight lines with, get a straight edge.
Oh
I'm gonna blow your mind.
This is gonna be really.
We're gonna get brains all over the floor.
Oh, woo! Okay, so.
That-
Set your straight edge on the origin.
I don't know.
I don't want to get straight in.
You literally just told them. Whoa, it's really big. Wait, should I connect them?
There we go.
Set your straight edge on the origin. From the origin, go through your original shape's point. And it should extend. You draw these lines lightly. Do not draw these super heavy. It should extend and go straight through your new point. Do that with all 4 of your points.
Wait, should I be connecting the points of the shape I made?
Yeah. Make a quadrilateral. Your new one.
Hold on, I gotta do this first.
And it should look like your quadrilateral is kind of like exploding out of the vertex.
Wait, no. Oh, I thought we just like keep going.
Whoa, that's weird.
So right now, the origin becomes what we call the center of dilation. Dilation is exactly how perspective works. Dilation, by definition, is an object getting bigger or larger, staying the same object. Are you okay? You can take the roll of tape back there. Getting bigger or larger by some multiplying factor. And that is our scale factor. So right here, our scale factor is what takes us from the original shape to the new shape. What is our scale factor here?
Right?
Yep.
Yeah.
We multiplied by 2. We have a scale factor of 2. To go from blue to red. Now, if we instead were asked to go from the red shape to the blue shape, what would be our scale factor? Ooh, not negative. There's never a negative scale factor. Thank you for saying that. It would be half. It is a multiplier. You're never going to multiply by negative because lengths can't be negative. So scale factor is always your multiplier. So, I know, I told you to do that before class. That's okay. I thought you were going to keep our secret, but it's...
I don't know if I'm supposed to look. These are all behind me. What?
So let's define dilation in your notes.
Wait, is mine supposed to look how it's looking right now?
Just one is twice as big. The problem is there's some overlap, so it looks a little awkward. Dilation. In your notes, please. Dilation is changing size. There's a lot of talking while I'm talking. Changing size, but not shape. Using a scale factor, which we know is a multiplier. We are using a a scale factor to change the size, not the shape. Scissors? What are you looking for? Get the snake, it would bit you. Are we good, Connie? Oh,
This is a baby snake.
did I tell you guys the weird one that Mrs. Goldring told me? Like making a silk purse out of a sow's ear.
Oh, yeah, I was right there.
Sow's ear.
Did you hear about the BOGO though?
Yeah.
There's
Buy one, get one. Buy one, get three free. It's free.
That's not BOGO. That's
It's called steel with the thing.
So, in Mr. Stanley's class, kids were checking out some geometry. And they came up with these questions. What happens when each coordinate is multiplied by half? What changes when the coordinates are multiplied by 1? What happens when both of the coordinates are multiplied by -1? I said that's not a scale factor. I didn't say you can't do it. I said lengths can't be negative, and that's why we can't use it as a scale factor. You try to scale a number and multiply by negative, you get negative lengths, and that would be really weird. You could say that a multiplier could be negative, but that doesn't make it a scale factor. So, try this. Throw this graph. Let's find out where these points are first and kind of agree on it. This looks like it's like -6. I'm going to make that smaller. Yeah, we're on 43 now. Where is this point? -6, 8. Yeah, sorry guys. Next year, kids will just have graph paper. We won't have line paper in here. Because I realized that. It's just better. 6, -4, I believe. And probably -2, -4.
Can we copy the graph?
Yep. Yep, the graph.
Okay, so it goes into 8. So I can make this one. Oh my god.
And if we want to make our life easy, let's say A, B, C. Let's process through these questions. What happens when we multiply by a fraction is probably the easiest question up here. Or what happens when we multiply by 1? That would be easy as well. But then what does happen when we multiply by like -2? Or what happens if we multiply by -1 even?
Then it's the yeah, it's the so it's literally just said multiply things. So how could we do multiply? Mr. Hudson just said you can't multiply by this.
No, I did not.
I know you said that.
I said a scale factor cannot be negative. That's asking what happens. Great.
So like
Yeah. Yeah.
It's the opposite of what is multiplied by 2. There we go. Yeah.
I wanted to be in a classroom with kids that stayed on task. We essentially talked about now in the last slide. Because we talked about
I'll just write it down for.
the last one. If you can't fit it, you don't have to graph it. But what would happen? If you know what happens when you multiply. But to graph the original one is beneficial at least because we're going to talk about what happens with all these different situations. Because we're going to throw some approximate points up here. When we do something to an object in geometry, we start to reference things based off primes. So points A, B, C, when I put one action on them, I then call those new points A prime, B prime, C prime. If I do another action to them, they become A double prime, B double prime, C double prime. We can go triple prime, and after that, we really often just make new points names because then you have too many primes. So Naya, what do you think happens when a shape is multiplied, or like when points are multiplied by 1/2? Yeah, what happens? What is it? It's bigger by 1/2. What do you mean? So if it was 4, now it's going to become 6.
So you take all of the coordinates of the shape and you multiply it by 1/2.
Every number gets multiplied by 1/2. Yep. What happens then to the shape?
No, it's smaller.
When using a scale factor less than 1,
It gets smaller.
always gets smaller. So if it was 1/8, it'd get really small. If it's 8/9, it still gets smaller, but not by much, right? So the closer it is to 1, the closer it is to its original. The closer it is to 0, still positive, it's going to get itty bitty. So 1/2 would be half the size. It would be inside of here. Well, shrunk down half the size. 8/9, because it's almost 1. Or 9/10 or 10/11. It'd be really tough. It'd be really, really hard. Like 0.8888. It'd be really, really tough. We'll get there. Well, law. What changes when the coordinates are multiplied by 1? So geometrically, yeah, it's exactly the same. It's where it was. Nothing moved. Nothing changed. Izzy's not here. Oh yeah, they talked to me. Zachary, what happens if I multiply these numbers by -1? What do you mean? What do you mean? Rotates 180 degrees. Zing, your hand's going through the ceiling.
So how I described it was positives changed to negatives and negatives changed to positives.
Yeah, so this becomes 6.
6 negative 8.
This becomes
2 and 4 to the opposite, and then negative 6 and positive. And then that makes it so that it does flip 180 degrees. But I just noticed that, of course, it just changed everything that was positive to negative.
so at 6, negative 8 would now be a point we would call A prime because we multiplied by negative 1. If I'm plotting those points, this is where prime comes in. I've done something to A. It relates back to A, but it's not A, it's A prime. And I can tell you how I got from A to A prime. And the same has to be true for B to B prime, C to C prime. So B prime is now 2, 4.
Oh no. So what's the definition of prime?
A point that has had something done to it. I mean, so it's notation. Don't think that it's specific to this. Prime is just a notation, meaning something's been done.
Okay.
So you, after you get a haircut, are Bilal prime. Like you have been changed. You're still you,
And then if you get
but
the
you've been
tattoo,
modified. Then if you go get a tattoo, then you're Bilal prime prime. Then if you know what I mean, like you're still you, but things have been done to you. And your mom will kill you. So negative 6, positive 4. That was a rough conversation. Not rough, but like when I called my mom and I was like, by the way, I'm going to go get a tattoo. What?
What is your tattoo?
This one's the one I can show you. It's for my mom and my niece. It's on my back. It says hope, faith, and love. And you symbol. So it's pink for breast cancer and orange for leukemia. Because my niece got diagnosed with childhood leukemia when she was 2. And had that till she was 6, I want to say. She's all clear now. She's like 13. She scares the bejeebus out of me. She has a boyfriend now. Her dad was in the Air Force, though, so I'm not that nervous. Dad will take care of it. Come see my guns. That's what happened when I met my father-in-law. So,
Yeah, mine's very.
this whole negative multiplier, are we sure that it rotated? Because a couple people said it flipped. It was pointing kind of up left, right? If we kind of like... That. Ooh, hold up, Piper, what?
When we did the reflecting flip thing, it wasn't over the other shape, it went over a line, but in this case, it just didn't go.
So what if it reflected x-axis and reflected down here? Where would it be pointing?
It would be pointing this way.
Yeah, down, left. If it reflected y-axis and flipped this way, it'd be pointing up, right. This was a rotation. So you should make a note of this in your notes. If we multiply by negative 1, it's a rotation 180 degrees, which is not a flip. A lot of people try to tell me, because when a person rotates 180 degrees, right, you've like flipped over. But that's not the same.
Not three-dimensional. It's
Yeah.
two-dimensional, so that doesn't work.
So wait, for all the marbles, what happens if we multiply by negative 2? Rachel, I think your hand is up first.
Okay. So you keep it like it was, or like all the negatives are positives, like all the positives.
So we do a rotation.
Yeah.
Okay.
And then you multiply all the numbers by 2.
So it's going to rotate and
Then get bigger.
and stretch, get bigger, right, by double, right? Yeah. So negative makes a rotation happen. The 2 makes a stretch, makes it scale up, makes it double in size.
So it doubles it and then finds the opposite of that double.
Or find the opposites because you rotate and then, yeah, it doesn't matter which order. Cool. Questions on this?
It's actually an interesting one.
So the negative 1, that's a rigid transformation, right? The size did not change, it just turned it. The negative 2, not rigid because it's stretched. Rigid keeps size the same. So, make a new question for the what happens if, or what happens when. Now remember, we can't add or subtract. That breaks the rules of geometry. You will not get a congruent shape. If we're looking for dilation, congruent shapes, we can only, well, okay. I see like a couple hairy eyeballs raised. I mean, we can add or subtract to individual points, like the translations. But if we add the same thing to everything, it doesn't work the same as multiplying. It does not dilate. We're trying to dilate here. So make your question, then make a guess, and then try it. Make your question, make your guess.
What happens if you divide by 0?
Well, the world explodes. Because you can't divide by 0. It's impossible.
Okay, zero.
Take something, divide it into no parts. Doesn't work.
Wait, would it work in other dimensions because technically they don't use the same?
Move into your
It has science and math.
Alright, for the benefit of moving quickly, sorry, 'cause we're running out of year, we're just going to move on past this actually. Sorry to cut you off and not give you a ton of time. Yeah, you destroy your shape. So you dilate it to nothing. You triple the size and rotate. So you rotate 180 and triple. Alright,
I wrote it down first.
undoing dilation.
Wait, we're on the next one.
Yes, I'm moving on to 622, but it's not going to affect your homework or anything. I'm just trying to get some more learning done.
I love to
So, Charlie multiplied each coordinate of a shape by 4. Right? Yeah, by 4. So I keep doing a lot of reading. This is the new shape. You need to determine where the original shape was. So essentially, you're working on A, but I phrased it differently. You need to figure out what the original shape was, like where the points of the original shape were. So here, I'll go ahead and label. Make your life easier.
Thank you.
We'll call these. Hey, hold up. If these are the points after something happened, right? Charlie already did something. We'll call this A prime, B prime, C prime, D prime. What we're asking you, where was A original? Where was B original? C original? D original?
Wait. What they are.
Fine, I'll challenge you. Do it with multiplication.
Calculator.
4, 8.
I didn't put your pie.
Oh, wait, so are you doing this at 16?
Oh, yeah.
It's still 4. Honestly, I think that's the only way you're going to do it. Wait, what's C?
Oh, 9.
9? Oh, man.
8. A is -1, 9. B is
I did.
Whoa, they're all
I've heard. Where's A?
A prime or A?
A. We already know. No, I wrote where I didn't want it to, and so -1, 1. Oh crap, that's like right there. B.
One, two.
Okay, 1, 2. Sweet. I'm a little off kilter. C.
2, 1.
I got it.
Oh, it's right.
Yeah.
And D.
1, 1.
I got it.
I got it. Oh my god.
What do you notice about the resulting quadrilateral? It's the same shape, okay? Yeah. It's a fourth of that shape. And now hold on, because you know it's a fourth of that shape, is the area a fourth? Is the area an eighth? Oh, I do know. Say it louder.
It's 16.
Do you know why?
Because it goes by 4 and it was already like 4 times 4 is 6. I don't know.
Little note out here.
Explain my thought process. 4 times 4 is 16. Yeah, 4 times 4 is 16, but I don't know what the other
The change in the area. You don't need to know this, but the change in the area, this is like a high school type topic more so, is your scale factor, because your scale factor acts linearly, your scale factor squared. So here, since the scale factor is 1/4, it becomes 1/16. Now, hold up. Can you not make a conjecture of why this shape landed on the original? Or why the original landed on the dilation? Not the switchy action. Would the triangle that we just looked at have done the same thing? We multiplied it by half? No, that didn't work. When you dilate. You know what I said? I didn't say anything, but you weren't paying attention to that.
You said when you die.
I did say when you dilate.
Not when you die. When you die.
Oh,
dilation
in your eyes.
If anything is on the origin, you're still going to involve the origin. Hey, Lana. Remember that conversation we had like 15 minutes ago? Okay. Because it doesn't seem like it. You know what I mean? Like, it seems almost like you're doing the exact opposite of what I would anticipate. Maybe it's just one of those Mondays and I'm just going to get confused. Probably me. Alright, we're out of time. So I'll take any questions you still got. I want to make sure we got. That is why it's called dilation. Hey guys, Naya just made the connection. That's why your eyes, your pupils dilate. They're changing size. Ellie's like, oh, ouch, oh!